Welcome, aspirants. Welcome to the capsule number 2 on electromagnetic waves. So you remember in the capsule number 1, we have discussed in detail all the basic properties of electromagnetic waves. I taught you if you know how to write magnetic field, how you can write magnetic field, and so on. I also gave you one assignment. Now we are going to cover capsule number 2, which is very, very important because in this capsule, we are going to learn about Maxwell equations. So Maxwell was the scientist who is the father of electromagnetic waves, you can say, or you can say the person who actually gave the idea of EM waves. These days, all the modern technology is based on electromagnetic waves. Either you talk about the radio waves, you talk about the microwaves, you talk about the light waves, all the communication which is happening, most of it is based on the EM waves. Satellite communication is done on EM waves. Weather forecasting is done using EM waves. So it is a very, very important milestone achieved by the humans, the discovery of EM waves. And the first person to give this idea was James Clerk Maxwell. And it is a very privilege that if you can know about this man, see the biography of James Clerk Maxwell on YouTube. So there are many beautiful videos available there. So with that said, let's see what Maxwell said. So before Maxwell, there were 4 equations that were already present. So one is divergence of electric field, one is curl of electric field, one is divergence of magnetic field, and one is curl of magnetic field. So these are the 4 equations that Maxwell saw when he started doing or understanding the electrodynamics. So his idea was to let's conclude everything which has been done in electromagnetism and make a one theory which explains the entire electromagnetism. But in that process, he actually discovered something which was much more important. So the first thing that he saw was the divergence of electric field, del dot E, which is equals to rho by epsilon naught. So del dot E equals to rho by epsilon naught, where rho is known as charge density, which is, you can say, charge per unit volume. Okay, what is this charge density as such? So you know that this law is nothing but Gauss law. If you want to know what is Gauss law in detail, you can see the course. In the course, I have done the lectures on Gauss law in detail. Okay, so in the course it is been covered, but now I'm going to cover it very in a rapid manner. That Gauss law defines that del dot E equals to rho by epsilon naught, and Gauss law can also be written as E dot dA closed integration of Q enclosed. So basically, Gauss law says that electric flux passing through any closed surface is equals to charge enclosed divided by epsilon. So how much charge is enclosed in that divided by epsilon. So I'm not going to go in detail of this because Gauss law is already covered in the lectures. So the very basic statement of Gauss law is that static charges produce electric field. Because if you have charge, you have electric field. That is what Gauss is trying to say. Yeah, he has put in it in a much more fancier words, and he has actually given a way to calculate this electric field. But the basic statement which he is mentioning is that if you have a static charges, it will produce the electric field. And the electric field that will be produced by the static charges is always conservative. It is conservative in nature. And it is also time independent. Means this electric field which has been produced by these charges does not depend upon time. It is independent of time. So if static charge is producing some sort of electric field, then that electric field will never change with time. That electric field will be constant with time. Okay, and that electric field will always be conservative. If you want to know the meanings of this conservative, then please watch the lectures which have already been taken in the course of PhysicsByAaryan. Okay, now let's move on. The second equation is what is del cross E. So del cross E is given by minus curly B by curly T, which can also be written as E dot dl closed line integration of minus d phi by dt. This is nothing but this is a statement of Faraday's law. So Faraday's law says if your magnetic field is changing with time, Then also you can produce electric field. So there are two methods to produce electric field. One is by the static charge. And second, that if you start changing your magnetic field with time, the electric field will be produced. So if you have a static charge, it will produce electric field. But let's say you do not have any charge. You have a magnetic field which is changing with time. Then also you will get an electric field. This is the second state. And you can clearly see that if you have E dot dl equals to minus curly phi by curly t, it basically means if you're changing the magnetic flux or magnetic field as such, you will get some electric field. But now the thing is, now the electric field that you will get is time varying. Means now in the previous case, when the static charge was producing the electric field, the field as such was not time dependent. But now the field that you will get means if you change the magnetic field, you will get electric field, but this electric field will depend upon time. It will depend upon time and it will not be conservative. So this is the second statement which Faraday saw. Then he went to the magnetic field. Then he saw what is the del dot B. So del dot B, or you can say the closed line area integration of B dot dA is always 0. So it basically says that, so always remember that B dot dA closed integration is nothing else, but it is magnetic flux. So I have already covered all these things in detail in the course, that what is this B dot dA, what is this del dot B, everything has been covered in one lecture in detail. So if you are not still getting it, please watch the course. And if you are watching this free on Capsule course, you can join the course and understand all those concepts. Okay, so let's see. So this law says that magnetic flux, let's say I have a closed area. So I have a sphere. There is no magnetic flux which is passing through it. No net magnetic flux. If some flux is coming out, the same flux is entering in. So if I have this area, whatever flux is coming out, the same flux is going in. Flux comes out because of north and comes in because of south. So if you have north inside this, the flux will come out. But if you have south inside it, flux will go in. So if the same amount of flux is coming out and same amount of flux is going in, basically it means that north and south are present in equal amount. And that is always what happens. North and south always exist together. Even if you have magnet and you cut it down. So you have magnet, one side is north, one side is south, and you cut it down. Now you don't have one north, one south. Now you have north, south, north, south. So every time you have a magnet, every time, does not matter how you have produced the magnet. Is it a bar magnet? Is it a current carrying wire? Whatever magnet you have, you will always have north and south together. You can never have north individually or south individually. It means south and north are always equal. It means magnetic monopoles does not exist. Monopoles means one pole cannot exist. Only south cannot exist. Only north cannot exist because of this law. So this was the third equation which the Maxwell had. Then the fourth one, he went on seeing what is del cross B. So del cross B was mu naught J. J is nothing but current per unit area. So you have some cylinder, current is flowing through it. And if you divide this current with this area, cross-sectional area, so you have this cylinder cross-section area, pi r square. So if you have this current coming in, so current per unit area will be equals to current density. However, B dot dl, if you convert this differential equation into integral equation, you will get B dot dl equals to nu naught times current enclosed. So basically what this Ampere law is saying, that the current is producing magnetic field. Or you can say the moving charges are producing magnetic field. If the charges starts on moving, means you have some current, then you will get a magnetic field. So this is a basic statement of Ampere's law. So in order to generate the magnetic field, what you have to do is you just have to make your charge moving. Or you can say you need the current. If you have the current, you have the magnetic field. So this is the basic statement of Ampere's. So this was the summary of the things that was already been done before the Maxwell enters the game. Okay, so once the Maxwell enters, the first thing that he observed was there was two problems in the Ampere-Circuital law. So the last statement which I mentioned is Ampere-Circuital law. First three equations he found is perfectly okay. There is no problem in those equations. But in the last equation, he found there are some problems, and I am mentioning two of the problems. So very two basic fundamental problems that he observed in the Ampere's law was number one. The law has some fundamental problem, and what that law is, let's say you have a capacitor. So the major problem was with the capacitor. If you think about the capacitor, so let me, before jumping into what capacitor has the problem, but before jumping in, let's go slow down and let's see what is capacitor. Capacitor has two metal plates, plate number one, plate number two. These both plates can contain some charge. So if you start giving some charge, both of these plates can occupy some charge. One plate will occupy plus Q, another plate will occupy minus Q. And now these are the two plates. It have some charge, it has some potential difference. Now what is happening is I am charging these plates. So these plates are not stable. So you have two plates, and in the middle you have dielectric material. Means between these two plates you have air, or let's say some insulator material is present between these two. So that current cannot flow through it. Means current is flowing, but charge as such is not moving from here to here, because in between there is a dielectric material. If that is the case, then what is happening here? So in the stable condition, what is happening? So these are the two plates. I start giving it charge. So let's say these are two plates here. So plate number one, plate number one, plate number two, and I have connected it to a battery. So initially plates have no charge. This plate has zero charge. This plate has zero charge. I connected it to the battery. Some positive charge started coming, more positive charge coming, more positive charge coming, more positive charge coming. And ultimately, this will have so much of positive charge. Then the next positive charge which is coming will get repelled. It will not be able to go and sit here. Because this plate got so much positive charge, then now if the more positive charge is trying to come and sit on this, it will not be able to sit. Why? Because this plate is now repelling that charge. Similarly, this plate, negative charge is going and sitting, negative charge is going and sitting, negative charge is going and sitting, and ultimately this will have so much negative charge that more negative charge which is coming will get repelled. So this is what is happening here. So ultimately a point comes when no more charge can be given. That is known as a capacity of the capacitors. Now, this was the maximum capacity of the capacitor to contain the charge. If we give more charge to the capacitor, it will repel it. It will not hold more charge. So when that statement comes, or when that equilibrium is coming, that no more charge can be given, the current will become zero. Why zero? Because now no more current is flowing. So it means the current in the circuit is zero. So when the capacity has been reached, equilibrium has been reached, then the current in the capacitor becomes zero. Let me give you a very basic example. Your phone battery. You have your phone. Okay, I have my phone. Now what is happening in this phone? This phone has a battery in it. Battery and capacitor are basically the same thing. Nothing much is different there. So this phone has a battery. Now I am charging the battery. So current is flowing. I have put in the plug and the current is flowing in the circuit. The battery is being charged. When it becomes 100%, the current will stop flowing, because now it cannot contain take in more charge. So the no more charge is being taken, then the current in the circuit will become zero. The current is flowing when it is charging, but the current is not flowing when it is not charging, when it is 100% charged. So that is something which I'm telling. So now I want you to think that we are in a condition where the current is flowing, means we are charging the capacitor. So we are basically charging. So it is still under charging. It is not 100% charged. It is still charging. It is 50 or 60% charged. Now I want you to take two empirical loops. One loop is this one. You can clearly see this is the loop. And you can clearly see that the current is going like this here, and then the current is coming like this. So you can clearly see that current is passing through this loop. How much current is passing through this loop? I. So if the current passes through the loop, you can clearly see that if the current is enclosed in the loop, so you have some loop, and within this loop the current is flowing, means this loop enclosed some current. This was the current going on, and I came up with the loop and I enclosed it. So if this loop enclosed some current, then what happens? The magnetic field exists. So because of this loop, if we think about this loop, the magnetic field does exist at this point. Do you agree with me? So this was the current flowing up. So let me give you a very basic idea. So let's say this is a plate. This is another plate. You can clearly say plate 1, plate 2. Between the plates, you have a dielectric material. So no direct current is flowing. Something is going on, but no direct current is flowing, or no conduction current is flowing. So this is the first plate, this is the second plate, and between the plates no current is there, and you have the current coming from this plate like this. You can clearly see the current is coming from this plate like this, right? And on this side and on this side, between these two plates, there is no current. This black pen is a current, right? Now what happens in this black current? This was the current, and I came and I enclosed this loop. You can clearly see I'm enclosing some current, black current I'm enclosing. So that is I. That is, it means if I have some current in this wire, in this loop, then the magnetic field will be there on this point, will be there on this point, will be there on this point. All the points on the loop will have the magnetic field. True fact. But now let's say I have the same kind of situation, but now I have loop. So this was a left plate, and this is a right plate, and this is the left plate. So, and current is like this. So now let's consider this current very close. Now I have loop like this. I have loop like this. So current is not passing through it. It is just coming till here, and it is not actually passing through this loop. So if you have this balloon kind of loop, can you clearly see this balloon kind of loop? Yeah, definitely the current is here, but it is not passing through it, because you have situation like this. Yes, it has current here, but it is not passing through this loop. So no current is enclosed in the loop, which is flowing through the loop. No current is there. So if you consider the loop number 1, then the current is there. But if you consider the loop number 2, then the current is not there. And both the loops have the common points. So these points are the common points. So according to the loop number 1, the magnetic field is there. According to the loop number 2, magnetic field is not there. So what is the situation? Is the magnetic field there, or is the magnetic field not there? What is happening? So Ampere's law had that problem. Ampere's law was not explaining that. Ampere's law did not explain that how this is happening. Also, there is a very major problem in charging of the resistor. If the current came here, then where does the current go? Because in the middle there is a dielectric material. Then how this current directly jumped from here to here? How this jumping happened? What is the physics behind this? That okay, current came till here, and then there was a dielectric material in between. So how the current went from one plate to another? That is also one of the questions. So that is the situation. So these two are the so this was the first problem in the Ampere's. Okay. Then Ampere's law don't work in the case of, so Ampere law is not working. And what we observed was, or what Maxwell observed, if it is static case, means now the current is constant. Now the current is not changing. So when you charge a capacitor, let's say you have this mobile phone and you are charging it. So when it is at 0%, you have seen that it goes very rapidly from 0% to 30%. If you are charging it, it will go very fast from 0% to 30%. Then it will go slowly to 30 to 40, more slow from 40 to 50, more slow from 50 to 60. So as your charged percentage increasing, the amount of current starts to reduce. Initially, the current was huge, then more, less, 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 less. And when it is 100% charge, current becomes 0. So more and more you charge it, the current will reduce. So the current is not constant. So if the current is constant, let's say all the time the same current is there, then the Ampere law works fine. Then there is no problem in Ampere's law. But in the situations like this, in the capacitor, charging of capacitor, so in magnetostatics, what we did, we defined the Ampere's law in magnetostatics. And in the magnetostatics, we were keeping our current constant. We were not changing our current with time. So Ampere law was working at that time. Why? Because our current was constant at that time. But now what is happening is we are changing our current. So as the percentage of battery in my phone keeps on increasing, my current keeps on reducing. And when it is 100% charged, my current becomes zero. So whenever my current is not constant with time, my Ampere's law will not work. I hope you understood this shit. Okay. So this is the 3 lines which I have written. Then comes the second problem. There is a very huge amount of symmetry problem is there. If you carefully see the electric field equation, they are fine. No problem is there in electric field equation. For example, you know this equation, Faraday law, del cross E equals to minus curly B by curly T. Which means if the magnetic field is changing with time, it will produce electric field. Fine, perfect. Now I'll take the divergence on both sides. So this will get divergence of curl, and this will be, let's say curly B, curly by curly T, let it be as such, and you will get del dot B. Now you already know that del dot B is always zero, right? Maxwell third equation, del dot B is zero. We read, right? The 4 equations that was given before him, which says that magnetic monopoles does not exist, is that del dot B is zero. So this side, right hand side is always zero. It is always going to be zero. And left hand side is also always going to be zero. Why? Because the divergence of curl is always zero. You know the vector algebra. Whenever you take the divergence of curl, it is always zero. And whenever you have del dot B, it is also always zero. So left hand side is always zero, right hand side is always zero. So perfect match in the equations. But if I do the same thing with the magnetic field equation or Ampere's law, so this is your Ampere's law. Del dot B, del cross B equals to nu naught J, means the current is producing magnetic field. Fine. That statement is okay. But now let's take the divergence on both sides. So del dot del cross B on this side and nu naught del cross J on this side. Obviously, left hand side is always going to be zero because the divergence of curl is always zero. But this side does not necessarily to be zero, because we have one equation known as equation of continuity, which says that del dot J equals to minus curly rho by curly T. This is known as the equation of continuity. I will have some words on this in the next page, but for now you have to accept the fact that this is known as equation of continuity and you cannot violate this equation. Never in physics it can be possible that you can violate this equation. Even in the higher order theories like string theory and all those situations, you have to respect this equation. Okay, why you have to respect, I will come to that. But you carefully see that this will be zero only if your charge does not depend upon time. Means your charge is not changing with time. Charge is not changing with time, so means current is not changing with time. If charge changes with time, then current will also change with time. So if your current is not changing with time, this is zero, and you want this to be zero. You want left hand side to be equal to right hand side, and if you want left hand and right hand side to be equal, your right hand side has to be zero, because left hand side is always zero. Because del and curl, divergence of curl is always zero. This is always going to be zero. If you want both sides to be equal, then this has to be equal, zero. So it means if your charge does not change with time, or your current does not change with time, in that situation, this thing is perfect. But if your charge is changing with time or your current is changing with time, then this equation does not work. Again, Ampere's law is not working for the situations in which the current is changing with time. It is only working for the conditions in which the current does not depend upon time. The current is constant with the time. So in both the problems, we saw the same cause root. The root of the problem was same. in the capacitor also, and in the equation of continuity also. Why the Ampere law is violating the continuity equation? The root cause is same, that the Ampere's law is not working when the currents are changing with time. So these were the two problems which Maxwell saw in the Ampere's law. And he definitely knew something is missing here. Before summarizing all the facts that he had, he observed that, okay, something is definitely wrong in Ampere's law. Then he asked a very smart question. And that question actually led him to a great discovery. And that question was, is if the changing magnetic field is producing electric field. So you already know this equation, that if the magnetic field changes with time, electric field is produced. So are we also getting the reverse effect? Means if we change the electric field, can we produce magnetic field? So if changing magnetic field produces electric field, so does the changing electric field will produce magnetic field? So the question is, does the changing electric field produces magnetic field? And that work has not been done before him. And when he did and developed this idea more, he found out that yes, answer is yes. And this is exactly what is missing. Exactly this is what is happening. Whenever the electric field is changing, it is producing magnetic field. Okay, and that is the missing key in this entire theory. And he put that gap. He removed that gap. He filled that gap with this missing piece. So this was a piece which was missing in the EMT, which was done before Maxwell. And he pulled up and pulled this piece in. Okay, and the piece was that yes, if your electric field is changing, means what do you mean by that? If your voltage is changing or your charge is changing, then what happening is you will generate a magnetic field. Generating magnetic field means generating current. Okay, so if the charge starts to change with time, let's say I have 2 coulomb charge, 3 coulomb, 4 coulomb, 5 coulomb, I'm continuously changing my charge, then I will start getting current, or you can say magnetic field. How? This is the question. If I have in this box, charges are not flowing. I am very, very specific with my words. If charge starts to flow, then so definitely we have current. No one can stop us. But let's say charge is not even flowing. No charge is flowing, but only the charge is changing with time. So initially I have 2 coulomb charge, 3 coulomb, 4 coulomb, 5 coulomb, 6 coulomb. The current starts to flow. Means you get a magnetic field. That is exactly what is happening in a mobile phone. So in the battery, charge is changing with time, 30%, 32%, 33%. So you have one metal plate, another metal plate, capacitor. So charge on the capacitors is changing, means electric field between them is changing with time. On what factors electric field depends, right? If I remind you that this is plate number 1, this is plate number 2, the electric field between the plates is sigma by epsilon naught. So if you are changing the charge or you are changing the sigma, you are changing the electric field. So electric field between this is changing. As the plates are getting more and more charged, the electric field between the plates is changing. As a result, magnetic field is produced, or you can say the current is produced between the plates. Why there is a current between the plates? Even though there is a material, the insulating material between them. That current is not the normal current. That current is not because of the flow of charge. That current is not because of the flow of charge. Insulator can stop the flow of charge. Insulator cannot stop the change of charge. If your charge as such starts to change with time, it is not flowing from one plate to another, it is just changing. 30% charging, 32% charging, 33% charging. Still there will be some current which is not in the form of flowing of charge. There is some sort of current, means the equivalent of current. Why? Because the changing electric field produces magnetic field. And magnetic field word means current. That is what is happening. That is why we have the current between the plates. Again, I'm saying when I say current between the plates, don't think that something is flowing from here to here. we have something equivalent to current, but it is not actual current. It is actual current, but it is not because of the flow of charges. It is because of the change of charges with time. Amount of charge is changing with time. If that is changing with time, electric field is changing with time. And if electric field is changing with time, it produces magnetic field. And if it produces magnetic field, it means it is equivalent to the current. Mic drop. That's all Amperes asked, and that is what your Maxwell asked, and that is what your Maxwell got. So he said, okay, let's fix Amperes law. So he started with the equation of continuity. Equation of continuity says that del dot J equals to minus curly rho by curly T. How much current is changing in this? So what is equation of continuity? I'm trying to explain to you this. Let's say you have some box. And in this box, what is happening? That current is changing through this box. Initially, there was 2 ampere current. Was here it is 2 ampere, 3 ampere, 4 ampere, 5. So in the left-hand side of this box, the current is 2 ampere. And on the right-hand side of the box, current is 3 ampere. So 2 current ampere entered, but the 3 ampere current left. How it is possible? How it is possible? There was a box in which 2 ampere current entered, but 3 ampere current left. So the charge is not conserved. Even though the entire circuit may be charge is conserved, but in this area, charge is not conserved. Then from where that extra one ampere current came? So let's say this box also had some stored charge in it, and it gave away some charge. This box already had, let's say, 5 coulomb charge. So 2 coulomb charge came, 3 coulomb charge left. It means 2 coulomb is this one, and 1 coulomb is because of this box. This box also had some charge. So this charge went with this. So how much charge is changing in this box? Means in this box, let's say initially 5 charge was there, and now 1 charge is gone, so only 4 is left. So if the current is changing, it means the charge in this box will also be changing. So if 2 coulomb charge came, 3 coulomb went out, it means this box must have to give 1 coulomb charge from himself. Otherwise, this is not possible. So basically, equation of continuity ensures that charge is conserved at all the points in the circuit. Not just overall, but at all the points also the charge should be conserved. That is known as the local conservation of the charge. Charge has to be globally conserved as well as charge has to be locally conserved. Here also the charge needs to be conserved. Here also charge needs to be conserved. Here also charge needs to be conserved. At all the points in the circuit, charge has to be conserved. And equation of continuity ensures that it is happening. Okay, that is why you cannot never violate equation of continuity, because you cannot violate the idea of conservation of charge, right? So he started with the conservation equation of continuity that says del dot J equals to minus curly rho by curly T. And this comes in exam. The question from the equation of continuity has been asked, so you need to remember this equation. Fine, let's move on. What is del dot A? E. Del dot E is rho by epsilon. Perfect statement. This is Gauss law. So let's keep rho on one side and del dot E on the other side. So this is your equation of continuity, and let's put the value of rho here. So rho is what? Epsilon naught del dot E. So what I do is I take this minus out, I take this del out, and I keep this curly by curly T inside. So on the left hand side, I have del dot J. On the right hand side, I have del dot minus epsilon naught curly E by curly T. And I took this on the other side. So I will get del dot J plus J epsilon naught curly rho by curly E by curly T, which is equals to 0. So this is the equation which I got. So the Ampere's law has somehow get fixed. How it get fixed? You remember the problem in Ampere law? The problem was that on the left hand side it was del dot del cross B, and on the left hand side it was nu naught del dot J. This side was also always 0, but this side was not always 0. Del dot J is not always 0, but del dot J plus epsilon naught curly E by curly T is always 0. It means we have to replace J with the J net. We cannot just use J because del dot J is not always 0, and we want left hand side and right hand side always 0. That was a problem number one in Amperes law. So we know that if we want this thing to be zero, then del dot j is not always zero. But del dot j plus epsilon naught curly E by curly T is always zero. So we have to replace j with the new j. And that new j is known as net current density, which is old j plus displacement current density. This thing is known as displacement current density. And how do you define that? This is this term. Epsilon naught, there is no negative sign here, sorry. Epsilon naught curly E by curly T. So if you add epsilon naught curly E by curly T into the net field, then your Ampere law is fixed. So what basically you can say is del dot J net is always zero. Del dot J is not zero, but del dot J net is always zero. And J net is made up of two things. One is J and one is epsilon naught curly E by curly T. This is known as free current density and this is known as displacement current density. Because now we learned that current is produced by two things. One is flow of charge. Flow of charge is this. And one is change of charge with time, which is this. You can clearly see electric field is changing here. So electric field is changing. It means magnetic field is produced. It means current is there. So current is also because of the flow of charge and also because of the change in electric field. This completes our story. And our Ampere law become del cross B equals to nu naught, not J, but J net. So our Ampere's law became del cross B equals to nu naught J plus nu naught epsilon naught curly E by curly T. Now our Ampere's law is complete. It basically states that the current can be produced in the two ways, or the magnetic field can be produced in the two ways. One, flow of charge, perfect. Second, change in electric field. This is what Maxwell did, fixing the Ampere's. So first three equations were already fixed. They were fine. Gauss law was fine. Faraday law was fine. Del dot B equals to 0 is fine. Magnetic monopole does not exist. Only thing was Ampere's law. So he fixed it, and the fixed form of Ampere's law is this. So I hope that you get the thing. Now let's do some of the problems. Okay. So this lecture is technically very sound. Means a lot of good concepts are there. And it is written in the Griffiths. Everything is written in the Griffiths, but not in the form I am explaining you. Now, if you will read the Griffiths, you will have the different kind of feeling. You will enjoy reading Griffiths. I can bet you. You will say, okay, this is what Griffith is trying to say. Because now you have got an idea what Griffith is trying to say. Because Griffith is written, but it is written by a foreign author. So understanding a foreign author is always a major problem. So now my suggestion will be, once you watch this lecture, go and read the Griffiths book. You will enjoy the book. You will fall in love with the book. And if you enjoy the book, thank me as well, because now you will, I hope that you will understand. Okay. Let's see the first question. So I have the capacitor, and across this capacitor, I have applied the AC voltage. AC voltage, you understand? The voltage which changes with time. And this AC voltage is equals to V naught cos omega t. So this is your voltage. Means it has initial voltage V naught and then it decreases, increases, decreases, increases like a cos wave. So voltage is continuously changing. They are asking what is the displacement current density through the capacitors. Means how much current density is there. So they are asking JD. And JD is what? Epsilon naught curly E by curly T. So first task is let's find the electric field. In case of capacitors, I have already covered this in my capacitors lecture. If you are not in the course, join the course. In the capacitor lecture, I have already taught that electric field is given by potential divided by D, where potential is the potential applied across the capacitor. Divided by D means the distance between the plates. So if you divide the potential with the distance between the plates, you get electric field. So what is your electric field? You put the value of V. V is what? V naught cos omega t, and divided by D. D is the distance between the plates. What is JD? JD is epsilon naught curly E by curly T. So epsilon naught will remain as such. V naught by d I remain as such. I have to do the differentiation of cos omega t. If I do that, I will get omega into sine omega t. So I am basically getting my answer as minus V naught epsilon naught omega divided by d into sine of omega t, which is your option number D. So this is your one of the previous year question. This is not something random question. So you can clearly see the questions are coming not very difficult. Let's see another question. So a parallel plate air gap capacitor is made up of two plates of area 10 centimeter square. So area of the plates is given and the distance between the plates. Each plate is at distance 0.8 mm. So both the plates are kept at a distance of 0.8 mm far away from each other. A sine wave. So you are using the sine wave and the amplitude of the sine wave is 10 volt. And this sine wave comes, goes, and like this. So the voltage is given by V naught sine omega t, and omega can be written as 2 pi into frequency, right? You remember omega is 2 pi nu or frequency. So omega t can be written as 2 pi ft. What is electric field? Again, so what they are asking basically, they are asking the amplitude. So have this word very carefully seen. Amplitude of displacement current density. I will explain you what is this amplitude means. So first of all, let's see what is displacement current density. Displacement current density is epsilon naught curly E by curly T. Electric field you have already found, which is potential divided by distance between the plates. So epsilon naught. So if you do the differentiation of electric field, you will get omega, or you can say 2 pi f into cos omega t. So this is your total current density, displacement current density. This is a varying term and this is the amplitude. So anything outside the cos is an amplitude. So this thing is an amplitude. Whenever you have wave like this, A cos something, this is known as the amplitude. So this is known as the amplitude of the wave. So amplitude of the wave is V naught epsilon naught 2 pi f by t. Rest I am putting on you. I'm not explaining you how to put the values. Put the values. If you put the values, the final answer that you will get is 0.03 milliampere per meter square, which is your option number A. So the same formula we used in both the questions, that two formulas basically, that electric field is potential divided by distance of the between the plates, and second formula is that JD is equals to epsilon naught curly E by curly T. So same formula in both the questions. So very simple. Third question is actually good one, and I think it is from the CSIR net question. Let's see what this question is trying to call us, or what he demands from us. So you have a dielectric medium of relative permittivity 5. So whenever you have some insulator or dielectric medium, whenever it is given to you, so you do not use the word epsilon naught, instead you use the word epsilon. So this is the permittivity in the free space, and this is the permittivity in the medium. And permittivity in the medium can be written as epsilon r into epsilon naught. And this epsilon r is known as relative permittivity. And this is given to you. So basically epsilon is given to you as 5 epsilon naught. So your epsilon, now your epsilon is not epsilon naught, it is 5 times epsilon. Because relative permittivity is 5. Okay. Amplitude of the displacement current. How much is the amplitude of the displacement current? So basically they are saying the amplitude of the displacement current and amplitude of the conduction current are same. Means the currents are produced because of two things. One, the charge is flowing, and whatever the current is coming because of the flow of charge, and whatever the current is coming because of the change of charge is same. So the charge because of the flow of, so the current because of the flow of charges, and current because of the change in charges with time is same. So the displacement current and conduction current is same. How do you define? So first of all, voltage is given to you. So they are saying, already saying that voltage is sinusoidal. So voltage is sinusoidal, and they are basically asking that frequency is also given to you, which is 1 megahertz. And they are asking what is the value of conductivity. So this material, what is the conductivity of this material? So the conduction current is very simple. You remember the Ohm's law in electricity? Ohm's law. Ohm's law in current electricity says that J conduction is equals to sigma times electric field. So whenever you have to say, if whenever someone asks what is the conduction current, you say J equals to sigma E. Sigma E is the conduction current density. current density. And what is conduction? Displacement current density. This is displacement current density. It is epsilon. Sorry, no, it is conduction only. So I am putting the value of E. So value of E is, so sigma comes as such. Value of E is V naught by D sine of 2 pi f into T. Simple. What is the amplitude? Amplitude is whatever is outside the sign, and that amplitude is sigma V naught by T. What about the displacement current density? Epsilon. Now I will not use epsilon naught. I will use epsilon. And epsilon is equals to 5 epsilon. We just saw that. And what about dE by dt? If you do dE by dt, you will get V naught by D 2 pi f cos pi omega t. What is the amplitude? This is the amplitude. So amplitude is 5 V naught by 2d. Why 2d? Because I multiply by 2 and divide by 2, so that this becomes 4 pi epsilon naught into f. So this is my amplitude of displacement current density. This is my amplitude of conduction current density. If I make both of these amplitudes same, then I can find the value of my sigma, which will come out to be 2.78 into 10 to the power minus 4. That is what my value is. So my option number A will be correct in that situation. So in this case, we learned something new, that the conduction current is actually sigma E. Rest everything was same. Electric field is V naught by D sine omega t. That is same. Conduction, displacement current density is same. Only thing that we learned in this question, which was new, is how to define conduction current. What is the current? Because of the flow of charge, which is sigma into E. Perfect. Let's see the next. So I think this will be the last question of today, and this is also from the CSIR net. So we have a solenoid. What is solenoid? If you don't know, I have covered it in the magnetostatics. If you are not the part of the course, join the course. And if you are already the part of the course, watch that lecture carefully if you do not remember what is solenoid and what is the magnetic field due to solenoid. Both of that is required. Okay. So I have a solenoid which has a radius capital R. Perfectly fine. I'm okay with that. And this solenoid has n number of turns per unit length. And the current is through this solenoid is changing with time. If the current is changing with time, something will happen. So if the current is changing with time, it means magnetic field is changing with time. And if magnetic field change with time, we get electric field. And that is what he is asking. That if the current is changing with time, what is the magnitude of the electric field? Find the what electric field will be produced. At what point he is asking? He is asking at distance r, which is lesser than capital R. So capital R is the your radius of the solenoid. He is asking somewhere inside. Means he is asking at the small r. So I will use which equation? I will use the Faraday law. Faraday law basically states that E dot dl equals to minus d by dt, or you can say minus d phi by dt, and phi can be written as area integration of B dot dA. Magnetic flux. Phi is nothing but magnetic flux. So E dot dA closed integration is equals to minus d by dt of area integration of B dot dA. So I need to do this closed line integration. And in this closed line integration, you will have some area also. Area also. So what is that line integration? So let's consider the small loop of radius small r. So consider the circular loop of radius small r. And what is the magnetic field inside the solenoid? Magnetic field inside the solenoid is given to you as nu naught times n times current. N is the number of turns per unit length, nu is the permeability, and I is the current. And this magnetic field is always along the axis. So this is always along the axis. Means this axis is k cap. So the magnetic field is also always along the k cap. So magnetic field can be written as nu naught I n I naught. What is I naught? So I is given to you. Current is given to you, right? Current is I naught sine omega t. You can clearly see that current is I naught sine omega t. So this value of current I have put here. So I get the value of my magnetic field. So E dot dl. So let's say your electric field is turning. So your loop is turning, right? E dot dl. So you are moving on this loop. You have the circular loop. Dl is the small amount of walk you have done on the loop. So you are moving on this loop. Dl, 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 dl. You complete the circle. Dl, 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 dl. You are moving on the loop. And this loop is rotating, means theta cap. You remember in the cylindrical axis, we have one r cap, we have one theta cap, and we have one k cap. R cap is radially outside, means this is an axis, this is r cap. And theta cap is rotating, k cap is this axis. So your electric field is rotating because your dl is also rotating. So if you want your E dot dl to be 0, means you have to, in whatever direction your dl is, so you have to move in that direction in whatever direction your dl is. So your dl is rotating, so your electric field is also rotating. So electric field is also like azimuthal or circular, because you have to follow the path of dl. Otherwise, dot product will become 0. If one vector is in this direction, one vector is in this direction, their dot product is 0. So you have to take the component which is in the direction of dl. Only those components are allowed which is in the direction of dl. So dl is rotating, so your electric field is also rotating. So E dot dl means electric field is constant, so let it be. So the area integration of dl means entire loop's length. What is the length of entire loop? 2 pi r. So E into 2 pi r minus d by dt b dot dA. In which direction your area vector is? Your area vector is perpendicular to loop. So this is your loop and your area vector is perpendicular to it. It means your area vector is actually along the z-axis. It means if your area vector is along z-axis, it means your magnetic field is also along z-axis, because you have to take your magnetic field in the direction of area vector. So if area vector is along z-axis, then your magnetic field also has to be along z-axis. Same logic, otherwise dot product will become 0. So your magnetic field can be in any direction, but only that will be non-zero, which is in the direction of area vector. So B is constant, so total area of the loop will be A. So let's say A. Right? So you do E into 2 pi r. B is constant, so you put the value of, no, B is not constant. So B is what? Nu naught N I naught. You can actually see what this is B naught. So you can do the dB by dt. If you do the dB by dt, you will get this thing. And I have also put the value of area, which is pi r. So now I can take this on this side, and my electric field will come out to be half omega nu naught N I naught R cos omega t, which is my option number D. So this question was new. We learned a lot of new concepts. Number one was, what is the magnetic field due to solenoid? Number two was, what will be the direction of electric field? What will be the direction of magnetic field? And how we use the Faraday law. Faraday law. This is nothing but Faraday law to find the electric field. So your magnetic field was changing, and as a result, electric field is produced. So that was all about the capsule number 2. I hope that you learned a lot in this capsule, and capsule 3 is also out soon. So keep watching these lectures. I hope you are learning in these lectures, and I will see you in the next class. Please read Griffith's book. Very important book for this chapter. So that's all. That's all for today. See you in the next class.